Good morning, everyone. Today we will see 01 knapsack problem. How to solve 01 knapsack problem using dynamic programming concept. Previously we discussed fractional knapsack problem that is solved using greedy approach. So 01 problem can be solved using dynamic programming approach. We will see what is dynamic programming, then knapsack problem. And dynamic programming is a problem-solving technique or method used for solving complex problems or like optimization problems. Optimization problem will give maximum value for maximization problem and minimum value for minimization problem. And it is particularly effective for optimization with recursive concept applications. The core idea is to solve subproblems only once and store the result in a table, and it will avoid the recomputation of subproblems that increase the efficiency of algorithmic approach. So dynamic programming plays important role in solving uh, optimization problems, and there are four key concepts in dynamic programming. Subproblem, the problem, complex problem is solved, divided into number of subproblems, and optimal substructure. Optimal solution for subproblem is calculated first, then it can be reused for finding the optimal solution to the whole problem. Then overlapping subproblems. Here this method is applicable where subproblem is occurred more than once. That is overlapping subproblems that is solved recursively. Uh, Example, Fibonacci computations to find the nth term in the Fibonacci series. Here the function Fibonacci of n that is called recursively with multiple inputs. So to avoid a recomputation of subproblems again and again, dynamic programming concept can be used. Memorization. That is, subproblem results are stored in a table that can be reused whenever the problem occurs more than once. So that time complexity is reduced from exponential to polynomial time. And we will see what is knapsack problem. The problem is there's a bag with the capacity and there are n number of items. Each item has weight and value. And we have to find the subset of items that fit into the knapsack with maximum value. This is example for maximization problems, optimization problem, maximization problem. Here we are finding a most valuable subset that fit into the knapsack. Input is there are n objects with the weight and value or profit. So O1, O2 are weight. W1 to Wn are weight of each objects, and profit or value for each object is given P1 to Pn. Here what's the constraint? So the total capacity of the item that put into the knapsack should be less than or equal to knapsack capacity. That is sigma xi. If the item is selected, xi value is 1. The item is not selected, we are not adding the weight, that value will be 0. And if you are adding item into the knapsack, add the weight of the items. The total weight of the item to be added in the knapsack should be less than or equal to capacity of the knapsack, where xi is greater than or equal to 0 or 1, or I is greater than or equal to 1. I varies from 1 to n number of items, and xi value is 0 or 1. And optimal solution is maximum of xi into pi. Xi value is either 0 or 1. If item is added, the xi value is 1. So we add the profit or value of the items that is to be added in the knapsack. That should be maximum. That is called optimal solution or objective function. And what's the output? Subset of items with the maximum profit or value that fit into the knapsack. See the example. There are two products. First product weight is 2, value is 14. Second product weight is 4, profit is 10. So we have to see the value of the item that fit into the knapsack. That is all maximization problem. And knapsack problem is a type of optimization. N weights and values are given. The problem is to find the subset of items that we can put it in the knapsack. Sum of weight is equal to or less than the capacity of the knapsack W, and the total value should be maximum. There are two types of knapsack problem: 01 knapsack problem and fractional knapsack problem. Here, fractional knapsack problem can be solved using greedy approach. Fractional means the part of the items can be taken. For example, 5 kg, 2 kg or 3 kg, the part of the item can be taken. This fraction of the item can be taken for adding into the knapsack. That is called fractional knapsack. What is 01 knapsack? 0 means we can't take the part of the item. The whole item can be added to the knapsack or not added to the knapsack. 1 means the whole item is added to the knapsack. 0 means the item is not added. Here we are not taking the part of the items. So we cannot divide the objects in 0 knapsacks. The whole item can be added or not added. Added means 1, the value is 1. Not added means 0. That's called 0 knapsack problem. Whole item can be added or not added. In the case of fractional knapsack, part of the item or fraction of the item can be considered for adding into the knapsack. So here in this video lecture, we are going to see about 01 knapsack problem using dynamic programming. So there are two types of approach in dynamic programming: top-down approach and bottom-up approach. Top-down means from base, we divide the problem into small problems till the base case. Here, the bottom-up approach means we are taking the base case for the solution. From the base case, we are deriving the result for the whole case. That is, the value are stored in a table that can be reused for calculating the objective or maximum value for the given problem. That is called bottom-up approach. It uses tabulation. And we start solving the smallest subproblem first. Then iteratively build up solution to the larger problem using a table, usually an array. It refers filling up a table in a systematic manner to avoid recursion. Here in this approach, there is no recursion. It uses only iterative or iteration statements. Looping statement, that is for loop, while loop. Here recursive function is not possible. In bottom-up approach, it uses iterative approach. All subproblems are stored in a table, so each computed only once. There is no need of computing the same subproblem again and again. It avoids recomputation of subproblems. And 01 knapsack problem, the problem statement. A list of n items are given, each item assigned with weight and value. Value or profit. So W of I, the array contains weight of ith item. The value VA represents value of ith item. And the knapsack capacity is given. The bag container capacity is given, that is capital W. So here our goal is to find the subset of items that fit into the knapsack with maximum profit or maximum value. The constraint is total weight of the item should be less than or equal to knapsack capacity. That is called constraint. And the objective is the item value should be maximum. Here 01 means the item can be taken or not considered for adding knapsack. 0 means not taken for adding into the knapsack. 1 means the object is taken to the knapsack. This is a problem statement. Next, we will see how to solve 01 knapsack problem using bottom-up approach in dynamic programming. We will see the general algorithm first, then we'll see one example. Define the table. Table name is TB, dynamic programming. We can give any user defined name. DP is a dynamic programming table. We are going to create one table. The size of the table is n plus 1 and w plus 1. N is number of items and w is knapsack capacity plus 1. So the array, two-dimensional array TP of I comma W stores the maximum value using the first items with the weight limit of W. Initially, step 2, we are assigning the rows 0th row and 0th column as 0 value. TP of 0 comma W for all weight, no items are selected, so value is 0. And for 0th column, TP I of 0 for 0 weight, capacity is 0, value is 0. And now we are going to fill the table using recurrence. Loop through items I equal to 1 to n. So this is a bottom-up approach, mainly works on iterations, looping statement. Loop through items I to 1. For item 1 to n, capacities from W1 to W. Capital W is knapsack capacity, small w is item weight. If weights of I minus 1 greater than W, item cannot be included. So the constraint is total weight of the item to be added should be less than or equal to knapsack capacity. So if it exceeds, if you are trying to add the item that weight is exceeds, we can't do it. Item cannot be included. So else, if it is possible, take maximum of including or excluding items. So here we have one formula. TP of I comma W is maximum of I minus 1 W comma values of I minus 1 plus TP of I minus 1 W minus weights of I minus 1. So we are taking the maximum value that is assigned to the TB table and return the result. Final answer is stored in the location n comma W, maximum value that can be put into the knapsack. So now we can trace the selected items to find the subset of items to be added. Okay, backtrack through TB dynamic programming table to find which items are included. So this is a general algorithm. Then we will see one example. Input, for example, there are 3 items. Values are 60, 10, 120. Weight of the items are 10, 20, 30. And the knapsack capacity is given capital 50. N equal to 3, number of items 3. And step 1, initialize the table. So 4 to 51 because we are taking 51 columns because the knapsack capacity is 50. So we are assigning from 0 to 51. 0 to 50, 51. And we create 4 rows. 3 items, we are creating 4 rows. So 4 rows with 51 columns. 4 rows is number of items. 51 is maximum knapsack capacity. And initialize 0th row and 0th column as 0 for all W and for all I. This initialization process. And now we are going to fill the values using the formula already we discussed. If we are adding item to the knapsack, the total weight should be less than or equal to knapsack capacity. If it is less than, we can add. We can find the maximum of value where it can be added. So we apply the formula maximum of 0W and W minus 10. Find the maximum that can be added. If you are adding item, the weight is exceeds, exclude the item that cannot be added in the knapsack. Results after row 1 for W 10 to 50 value becomes 60 initial value. And iteration 2 for item 2. First we are taking item 1 by 1. Iteration 1 we are taking first item and second whether we are adding item or not. And for item 2, value equal to 100 and weight is 20. For W from 0 to 50, if W is less than 20, apply the formula, find the values. So then after finding the value, we are going to fill the second row. That's at W equal to 30. We are finding maximum 160 and W equal to 50. Maximum is 160. So that value can be updated in the TB table. And For each item 1 and 3, value 60, weight 10, value 120, weight 30. So for W from 0 to 50, if W is less than 20, we can take the minimum value. And otherwise, we can take the maximum value. And so which one is maximum that can be considered? So in this case, the maximum value is 220. So there is a final result. And this is a dynamic programming table. This is a partial view. So 0 to 50. So we have the knapsack capacity 50. So we have 50 columns and we have 3 items. So number of rows will be 4, 0, 1, 2, 3. So the first last location TB of 3, 50. That location has the maximum value of subset of items that can be added to the knapsack. So maximum value is 220, that is stored in TB 3, 50. That's the final answer. And what are the applications of zero one knapsack problem? So for finding resource allocation, um, so in the industry we have different resources. How we can effectively assign resources for utilizations and investment planning. And there are many organizations that are expecting monies to be invested for share marketing and all. So that type of planning, it uses zero knapsack problem. And supply chain management deals with how the product can be transferred from producer to the customer and the agent, how it will reach the customers. And the cryptography, it's mainly for transferring data in a secured manner. Even video game designs. So video game design also zero knapsack problem is used. So these are the important application area where the problem zero one knapsack can be applied. So the overall conclusion is how we can apply zero one knapsack problem for solving resource utilization allocation problems. The problem can be solved using dynamic programming, using bottom to top approach. Thank you.